Okay, here's example 610, the traction device. Now, I've never had the misfortune of having one of these used on me, but I guess from what I understand is that if you break your leg or your arm, in many cases it helps it heal if you actually have tension put on that limb right there. So this person's foot, there is tension being applied to the bottom of his or her foot by way of this pulley. The weight of this mass right here is creating a tension in the string, so it pulls the pulley towards the person, or it pulls the string away from the person, which applies tension to your foot. There's a big assumption right here, and the assumption is that this whole system, the net force, I don't like that color already. I'm going to do it in blue. The net force on that whole system is 0 newtons. Why? Well, because we don't want this system to be moving. We want it to be static. As uncomfortable as it is for a person to be sitting there with this tension applied to their limb, it would be even more uncomfortable if this system were constantly moving. So the assumption here is that we have a stationary ceiling, we have a stationary patient in the bed, hopefully, and that means that this mass right here also must be stationary. All right, so the question is, what must that mass be? Find the value of mass m. All right, well, why do we care about that? Well, because this mass m right here is creating a downwards force. It's weight force, right? mg, straight down. And also, if that mass is not moving, it means there must be some other force acting upwards against it to keep it from moving. And there certainly is. That force is what we call tension in the string. And why is the string not moving? Well, if you follow it all the way up, it's ultimately attached to the ceiling right there, which we're thankful the ceiling isn't moving. All right, and so the ceiling is really, through this string, providing the tension or the force to prevent that mass from moving down any further. In the process, it's also going to be applying tension to your leg, hopefully to help it heal. Okay? Like we said before, tension acts 2 different ways in each string component right here. All right, and it is the same force throughout. You can't have more tension in this string and less tension in that string. The string is feeling equal tension all the way through. We're assuming here that the pulleys don't really create any friction or anything, or cause the string to hang up. The pulleys simply redirect that force around corners so it can go to where we want it to go. All right, and so the first assumption is this whole system is stationary. This mass right here is not, excuse me, is not moving. The other thing that we're told is that in order for this person's leg to be healed properly, they need to experience 165 newtons of force in their leg right there. All right, so you look at this setup right here with this, the tension force in this and this pulley right here. It kind of makes it look like the foot wants to be pulled this way. All right, that's the tension force applied by the string. So in order for the foot not to go somewhere, the person needs to pull back with their foot with the equal number of newtons. And so that's what causes the leg to stretch out and heal. All right, so the person needs to feel 165 newtons, which means that between these 2 strings right here, they need to apply the exact same amount of force in the opposite direction. All right, now let's take a look at just the mass for a second. All right, and then we'll go to the next page and deal with the foot. For the mass M. It looks like massum, but mass M. All right, let's take a look at it and see what that tension force has to be in the string. Well, if the net force of the system on that mass is 0 newtons, that is, it's not accelerating at all, then we can say, all right, let's look at our component forces. All right, mg, don't know what that is because we don't know what m is. We're actually solving for that. and we have our upward force, T tension right there. All right, so that we can say the other way, we can say the net force on that, you might say in the component form on that mass, mass, there we go, is T is up, so it's positive, and mg, or the weight force, is negative right there. Well, you probably see where this is going. If these two statements for net force are equal to the same thing, that's both, it's just this two different ways of stating the net force, then we can say, all right, the tension in the string minus mg, the weight force of the mass, has to equal 0. 0 newtons. They balance out to 0 newtons so that this mass doesn't go anywhere. It just hangs there. Which also means that if we move our mg over, that means the tension in the string all throughout the string has to be equal to mg. The mass of that mass times acceleration of gravity. Let's dotted line box that right there. Because what we're going to do is, in the next part of the problem, as we look at the foot itself, oops, I don't really want to do that, but that's okay. As we look at the foot itself, we have tension in this string and tension in this string, both applying forces that that cause the foot to feel pulled. Okay, so wherever we have tension here and here, we're going to be able to substitute in mg. That tension in the string is mg. That tension in the string is going to be mg, and that's what we're going to look at for the part of the problem where we actually address the foot. All right, so I'm going to go to the next next slide right here. Sort of redraw this. Okay, so here's our foot, and I'm going to draw this cast on it. All right, so something kind of like, what's going on here? Why can't I draw? There we go. All right, so there's your cast. There's a guy's toe sticking out. Okay, that person needs to feel 165 newtons of tug. All right, 165 newtons, and we're just going to call that F, the force F. I should write it up top there. 165 newtons. Which also means, and I'll erase that here, that the weight force, that is the force of tension. So here's a little pulley right there. Oh, I'm going to make that. What should I make that? I'll make that red. Here's our pulley, okay, and the tension force in that string is going that way, and both of these angles right here are 40 degrees. 40 degrees. All right, so that's T tension and T tension. But as you recall, as we said before, the tension in the string is actually the weight force of that mass, right? mg. And mg. That right there, that mass that is down here somewhere, down below, we're not drawing it because we're dealing with the foot, is creating that tension in the string that is bending around corners right there. So, we know that the tension in the string has to be equal to mg. All right, that's helpful. But really, what's causing the person to feel a pull in the horizontal direction right here? Well, they're feeling a pull because this force here, tension, is at an angle, and it has a horizontal component. And so does this. This tension right here is at an angle and has both a vertical and a horizontal component right here. So what could we do to find the value of those forces? All right. Well, we have the hypotenuse, essentially, and we have the angle right here. So we could say that it would be T times a cosine of 40. That's how many newtons are kind of pulling horizontally because this tension string is at an angle. And this one too. T cosine 40 degrees. All right, so the tension in this string and the tension in this string are both kind of pulling horizontally on that person's foot. So we can say this. We can make a statement about the net force of the person's foot. And you know what? I got a lot of space down here. I'm going to just do it down here. The net force on the foot. Well, actually, first of all, what do we want the net force on the foot to be? We want it to be 0, right? We don't want it to go anywhere. We don't want there to be any acceleration. So that on the foot as a system. The system is not moving. That's good. All right? But like I was saying just a second ago, what about the net force on the foot as components? All right, we've got a couple forces acting on the foot in the horizontal right here. Let's see. We need to establish which is going to be positive and negative. Let's say I'll make this direction positive and this direction negative. All right, that means that we've got t cosine 40 plus another t cosine 40, right? Because that string is applying a force 2 different times as it bends around the pulley. Minus 165 newtons. That's this force right here that is required for the person to feel. All right? Once again, since both of these statements are equal, then that means we can say that t cosine 40 plus t cosine 40 minus 165 newtons has to equal 0. 0 newtons. Again, why is that? Because we don't want the foot to actually move anywhere. We just want all the forces on the foot to create tension in the foot so that it will heal. All right. Now recall that we're still trying to find out what that mass is that is required to create that tension to create the appropriate pull in the foot. Well, as we said up here, we said the tension in the string is actually caused by the mass times gravity of that mass, that weight, you might say. So why don't we just substitute that in? All right, so we're going to take mg and substitute it in for wherever t is right here. So mg cosine 40 plus mg cosine 40 minus 165 newtons equals 0. Okay? All right, well, remember, we're solving for mass, right? Solving for the mass. So let's see if we can separate that out and then kind of clean up our equation here a little bit. All right? I see these, we're just doing algebra right now, by the way. I see both of these statements right here as having m in front of them. Now this one doesn't, so what I'm going to do is, in fact, I'm going to just rewrite that mg cosine 40 plus mg cosine 40. And I'm going to move this 165 over to the other side, right? Equals 165 newtons. These two forces right here, this guy and this guy, has to equal out to 165 newtons, so that's what the person feels. All right? What we can do is, well, let's factor out then that m. We're solving for the m, right? Mass times, let's put everything else in the parentheses, g cosine 40 plus g cosine 40 equals 165 newtons. And you can see this is going to become a lot easier. I'm kind of running out of space at the bottom right here. Let's clean this up a little bit, and in fact, I'm going to call this 2g cosine 40, right, because you're just adding them together. And then this whole thing right here, so we get m by itself, this whole thing we're going to take and just divide under the other side. So our final statement, I'm going to write it up here at the top right here. So I'll draw an arrow up, and all right, is going to be mass equals 165 newtons divided by 2g cosine 40 degrees. All right, that's going to be our statement for solving for the mass. The required mass such that this system And these tension forces right here at 40-degree angles creates the right amount of force on this person's foot so that they feel the tension and then the foot doesn't go anywhere. So let's just plug and play now. The mass is going to be 165 divided by 2 times G is 9.81, right? Meters per second squared. Times a cosine of 40 degrees. All that is in the denominator right there. And the required mass for all that, I calculate to be 10.9. It's going to round up, isn't it? Sorry. 11. I'll just say 11.0. Oh, not newtons. Sorry. Mass is not newtons. Mass is kilograms, right? 11.0 kilograms. And that is the mass required to create the tension, to create the forces at those angles right there that creates the pull in the person's foot that allows it to heal. So, that was kind of, I kind of did that the long way. You may find shorter ways to do it, but any way you do this, always set up a free body diagram, sum up your forces in the x and in the y direction if necessary, and write your net force 2 different ways. Write the net force on the system that you're dealing with, and also write the net force on the thing that you're dealing with as a function of components. That is all the various forces that are acting in the positive and in the negative direction. So, I hope that helps. Once again, please be sure to contact me if this does not make sense to you. I'll be glad to go over it with you again. And in the meantime, thanks for watching. I'll see you on the next one.